Hello, ladies and gents. So today we have our second to last test to determine if a series will converge or diverge. Up till now, here's the sheet that I've given you, but we have the nth term test that tests for divergence. We talked about infinite geometric series. We did the integral test. We did the p-series test. We, last lesson, did direct comparison and limit comparison, and we have two left. Today is all about the alternating series test. And then the last lesson, the last test, we'll do the ratio test. So we have two left, and today is all about the alternating series test. Okay, so I'm going to jump over to the notes. And alternating sequences came up when we initially did the first lesson on sequences, when we had that -1 to the nth or that -1 to the n plus first power, the terms will alternate sign. Like it'll go positive, negative, positive, negative, positive, or it could start negative, positive, but term by term, the terms alternate in sign. So up to now, the series we've dealt with have had positive terms. Well, in this section and beyond, we're going to talk about series that have both positive and negative terms and how to determine if they converge or diverge. The one we're going to focus on the most are alternating series where the terms alternate in sign. Okay, so here is the alternating series test. Typically, you're going to identify that you have to use the test if you see the -1 to the n plus 1 or the -1 to the nth. When you identify that, that's how you know you're dealing with an alternating series. I say typically because there can be cases that are alternating, but they don't exactly look like this. We'll look at that as our last example. But this is pretty much what you're going to see most of the time. The nice thing is all of the determinations, the analysis is going to be done with the other part of the series, not the -1 to the n or -1 to the n plus 1. Like this just identifies that we're dealing with an alternating series, but all of our analysis is done, if you'll notice, with the rest of the stuff, the a sub n, a sub n, a sub n. So if you look at the examples here, like our analysis is going to be with the 1 over n, the 1 over 5 to the n, the n over natural log of n, so all of the other stuff. So here is what needs to happen. So the other stuff has to be positive terms. Like ignore the -1 to the n. The other thing has to have positive terms to use this test. The series will converge if the two conditions are met. So the other stuff, I don't know if there's a name for that, but the other stuff has to pass the nth term test for divergence. Basically, as n goes to infinity, the other stuff, the other terms have to eventually go to 0. Like you have to eventually be adding nothing. So that's the nth term. The other thing is interesting how they notate it, but the sequence a sub n has to be greater than or equal to the next term. Basically, the other stuff, term by term, the terms have to be decreasing, is what this is saying. Now, the reason they don't just say a sub n is decreasing is because these functions these are not continuous things. Like these are discrete terms. They're not in terms of function notation that are decreasing. But essentially, to wrap your brain around it, like this 1 over n, term by term has to eventually be decreasing. That's what this is saying right here. Now let's do some examples to show this. So it says, determine the convergence or divergence of the following series. Well, first of all, I know we're dealing with an alternating series because of this notation right here. And you can even see it, like if we plug 1, 2, 3, 4, 5 in, which I like to do a lot of times just to see what the series looks like. But if I plug 1 in for n, I'm going to get -1 squared, so positive 1, times 1. Like the first term is 1. And then if I plug 2 in for n, well, -1 to the third is -1 times a half, so -1/2. My pen is dying. If I plug 3 in for n, well, then it's going to be positive 1/3. And then it's going to be -1/4, and so on. And so we can see that alternating behavior happening. So now all of our analysis is with this right here. We're going to let a sub n equal 1 over n, and all of our analysis is going to be with this. So the first thing that needs to be happening is we need this to be greater than 0. Eventually, we need this to have positive terms. And it will, our starting value is n equal 1. And this will always be positive for any n value 1 or more. So this is greater than 0 for n greater than or equal to 1. So that's the first check. That's like the condition to even apply the test. Then the two things that need to be true, we have to verify it. We need the limit, so number 1, we need the limit of this, 1 over n, as n goes to infinity to be 0. This is us essentially applying the nth term test for divergence. Well, this does equal 0, so check. And then the next thing we need to be true is we need the next term to be less than or equal to the previous term eventually. It says for all n, kind of like we talked about the other day, it just has to eventually be true. For some n greater than or equal to 1, or eventually for some n greater than or equal to 3. I mean, it could even be for n greater than or equal to 1,000,000. It just has to eventually be true. So the way we notate that is this. We need a sub n plus 1 to be less than or equal to a sub n. Well, for the next term, the n plus first term, we go to our a sub n and we replace any n with n plus 1 instead. So a sub n plus 1, if I plug n plus 1 in for n here, that would be 1 over n plus 1. And we need that to be less than or equal to a sub n. Well, we talked the other day about how if you're comparing two fractions, if the tops are the same, if the top numbers are the same, and you're comparing two fractions, the bigger you make the denominator, the less this fraction is compared to this one. So we can make a very eyeball test analysis that this is true for n greater than or equal to 1. So since these two things are true, then our conclusion is this series converges. So therefore, the series of n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n converges by the alternating series test. Now this one is interesting. I want to explain why this is interesting here. So we've talked about the harmonic series. This is going to be a good thing for you guys. So we've talked about the harmonic series. The harmonic series, just 1 over n, this diverges. And this is one that we don't need to run a test for. This is one to be known that this diverges. Well, interestingly, the alternating harmonic series converges. So if we just did 1 plus a half plus a third plus a fourth plus a fifth, if these were all positive, this would actually diverge. But when these terms alternate in sign, the alternating harmonic series converges. And these are two that we can just know. This has come up in discussion. If you recognize or see the alternating harmonic series, you can just say this is the alternating harmonic series and it converges. You don't have to run through your tests right here. And sometimes that comes up on an FRQ where you just state that. It's just one that is known to be true and you can just state it. So the alternating converges, harmonic diverges. Let's look at example 2. Okay, so we know it's going to be alternating because we have the negative 1 to the n. So all of our analysis is with the, imagine there's a 1 on top here, is 1 over 5 to the n. That's going to be our a sub n. And we need three things to be true. First of all, we need this to be greater than 0. We need this to be positive terms. And we're only dealing with n from 1 to infinity, positive n values, which means this is true. So check. Then we need the limit as n goes to infinity of 1 over 5 to the n to be 0. The nth term test for divergence. If I plug infinity in, air quotes, you can't plug it in, but as n gets really big, this is going to approach 0. Check. And then the last thing that has to be true is the next term has to eventually always be less than or equal to the previous term. So we're dealing with 1 over 5 to the n. And the way we're going to notate this, we're going to plug n plus 1 in for n right here. So it's 1 over 5 to the n plus 1. That's the next term. Is that less than or equal to 1 over 5 to the n? And yeah, we have the same numerator. This denominator is bigger than this one. So true. Therefore, the series converges by the alternating series test. All right. Next one. Again, we have an alternating series. Surprise, surprise, negative 1 to the n times n over natural log of n. Okay. So the other stuff is n over natural log of n. We need that to be greater than 0. And that will be, because these are just positive n values. Positives over positives are positive. The next thing we need to be true, we need the limit of n over natural log of n as n goes to infinity to be 0. Now, this is interesting. The other ones, we could pretty much do a really quick analysis and eyeball test. You know, we know that it's going to equal 0. This one, if you plug in infinity, you're going to get infinity on top and infinity on bottom. So we don't know if this equals 0. Infinity over infinity is an indeterminate form. It's inconclusive. We've talked about L'Hopital's rule. L'Hopital's rule can be used on indeterminate forms for limits. Typically, it's when we get 0 over 0. Like, that's typically what happens. But it also works for infinity over infinity. We can apply L'Hopital's rule. And that's what we're going to have to do here. To evaluate this limit, I have to take the derivative of the top, the derivative of the bottom, and then reevaluate it. So by L'Hopital's rule, this is going to be, well, the derivative of n is just 1. The derivative of natural log of n is 1 over n. 1 divided by 1 over n is just n. So this is the same as the limit as n goes to infinity of n. And if I would plug in infinity here, this obviously is not 0. That's what we need to happen, right? Our test says this has to equal 0, and this doesn't equal 0. And so that means it failed just the first test. So this series diverges. So if you go to evaluate the limit and you can't just really quickly analyze, oftentimes L'Hopital's rule is going to be needed. All right, couple more. We have another alternating series. Okay, so our other stuff is natural log of n over n. That's our other stuff. We need that to be greater than 0. It is. Check number 1, we need the limit of natural log of n over n as n goes to infinity to be 0. Keep in mind, when, on multiple choice questions, guys, you can do really shorthand analysis. You're trying to work through these quickly. I get that. If you're doing a free response, make sure you guys are doing very nice, neat mathematical notation. Well, again, on this one, if I would plug in infinity, I would get infinity over infinity. So we have to do L'Hopital's rule. The derivative of natural log of n is 1 over n. The derivative of n is 1, so it's just like this is over 1. So if you're dividing something by 1, there's no need to actually write it. And so then, if I think about n going to infinity, this does equal 0. So check for the first one. The next thing we need the next term to be less than or equal to the previous. So again, when we are thinking about the next term, the n plus, I don't know if you say like n plus first term or n plus 1th. That doesn't sound right. It's got to be n plus first term. I don't know why I was even debating it. N plus 1th? That's just silly. Okay, so I'm going to plug n plus 1 into each of these n's here and here. N plus 1 into both. So I'm going to have the natural log of n plus 1, the next term, over n plus 1. And I need that to be less than or equal to natural log of n over n. Now this one is a little more frustrating or difficult than the previous. The previous ones, when we get to that step, the top numbers are the same, and so we're really just saying, oh, the bottom's bigger, so this is true. On the first two that we did. This one, I don't know if this is true. Right? I didn't put an n here. I thought that looked kind of weird. I don't know if this is true. I mean, you're probably going to sit there, and if it's multiple choice, you're going to be like, well, check. But you don't know. Mm-hmm. And so here is what's really happening. We can't eyeball test this one. And I mentioned this at the beginning. Really what we're trying to figure out is this thing decreasing? Like, is it eventually decreasing? That's really what we're after. And I mentioned the reason they use this notation is because these are discrete terms. So they're not going to use the word decreasing because that doesn't make sense mathematically. Like, you decrease on intervals, not like discretely. But what we can do is this. If we want to see if this related function is decreasing, we can actually apply the first derivative test. We can treat this like it is a function, find the first derivative, find our critical numbers, and see if this function is actually decreasing for some n value. So that's what we're going to do. We're going to let f of x equal natural log of x over x. We're going to think about this as a function, a continuous function instead, and see if it is eventually decreasing. And if it is, then this check passes. So first thing we need to find is the derivative. Quotient rule, low, d high, minus high, d low, over low, low. So that equals 1 minus natural log of x over x squared. And we're trying to find our critical numbers. I want to figure out what makes the top 0, what makes the bottom 0. That's what we're after. So let's set 1 minus natural log of x equal to 0. And really, you're just thinking, what makes this right here? There's a couple ways you can do this, but whatever makes this be 1, then this equation is going to be true. So essentially, you're thinking natural log of what equals 1. And hopefully, we know our natural log stuff, but that's e. The natural log of e equals 1. Let's say you were like, I don't know if I would actually think about that. Well, you could add natural log of x over, and then you can switch this to exponent form, right? The base is e, so e to the first equals x, so e equals x. All right. If we're thinking about what makes the denominator 0, well, that's just 0. Remember, that's technically not a critical number because it's not in the domain of the original function. But even numbers, even discontinuities on f, we always have to account for them on our sign charts because the sign of f prime could change on either side of a discontinuity. We're only after positive x values anyway, but I'm going to put 0 and I'm going to put e. And again, I'm just trying to make sure that eventually this function is decreasing. It doesn't have to be just for n greater than or equal to 1, it just has to eventually be decreasing. Well, if I plug in, I don't care about negatives because n is from 1 to infinity. So if I plug in, let's say 1, because 1 is between 0 and e. If I plug in 1 for f prime, I'm going to get, well, natural log of 1 is 0. So 1 minus 0 is 1 over 1. That's positive. So it's increasing. F is increasing from 0 to e. Well, that's not good so far because we need it to be decreasing. Well, let's plug in a number bigger than e. So you could use 3 or a billion. Let's do a billion. So 1 minus natural log of a billion, that's going to be bigger than 1. So 1 minus a big number is negative, over a billion squared is negative. And that's a good thing, because we were trying to show that eventually this function was decreasing. N is defined as integers, so basically what we would say is this. So a sub n plus 1, the next term, is less than or equal to a sub n, but it's not for n greater than or equal to 1. It's past e, but n is defined as integers, so we can just say for n greater than or equal to 3. E is 2.7 something. So we can say this is true, and it's true for every n value greater than or equal to 3. So check. So we met our conditions. Therefore, the series converges. Good stuff. I can't promise they're all going to be like this, but I want to make sure that you get a little mixture of fun. Last one. So this one, you don't see the -1 to the n or -1 to the n plus 1 show up, right? So you might look at this and be like, well, crap. But this is why I really like expanding series out sometimes, just to get a better understanding of what's happening. So let's kind of do that. If I plug in 1 for n, let's see what the first term is. Well, I would get cosine of pi, so that's -1 over 1. So that's -1. First term's -1. If I plug 2 in for n, well, then I get cosine of 2 pi, which is 1 over 2, so positive 1/2. Then if I plug 3 in for n, cosine of 3 pi is -1 over 3, so -1/3. And you can see what's going to be happening. We get positive 1/4, -1/5, ... Goes on forever. So we can see this actually is an alternating series, even though it didn't show up like normal. But basically, the cosine of n pi is kind of taking place of our -1 to the n type of thing. Like, that's the thing that's causing the alternating, which means the 1 over n is the other stuff. So we already know this converges because this is the alternating harmonic series. That was the very first example we did, and this is a conclusion that we can draw. This converges. We are going to go through our tests nonetheless, but very quickly. We've already done this. But that means our other stuff is 1 over n. The alternating part was cosine of n pi. This is the other stuff. This is greater than 0. And this one's pretty easy. We already did it, actually. But we need the other stuff to go to 0. It does. And then we need the next term to be less than the previous. And we already did this one. That's true for n greater than or equal to 1. Therefore, the series converges. All right. We are going to have one more test, the ratio test, which it's kind of fun. There's a lot of algebra involved, but it is kind of fun. It deals with like factorials and things like that, but we'll get there. All right, let me know if you have any questions. Peace out.